Howdy folks. Today we're going to take a look at state machines. State machines are a system that you can use to move objects between various states in a deterministic way. They're very popular with video game AI as well as programming things like language parsing and regular expressions. Let's get into it. So to start off with, the founding portion of a state machine is the state. These are the different states that an object in this machine can be in. Objects that are using the state machine can't be in any other state. So here we have scout, track, chase, and fight, which could be for an enemy guard, for instance. The second part is the connections. So every state has connections to every other state. Some of those connections can be bidirectional, some of them are one way. For example, scout, when a guard is in scout mode, they could move between track to track or chase. If they're tracking, they could move to chase, and from chase they can move back to track, but from those two places they'll never go back to scout. From chase, individually, they could go to fight, and from fight they could go back to track or scout. These are all state transitions. Now those transitions are actions. So these are various things that could happen in your world or your context that would cause this state machine to move to that new state. If you're doing language parsing, it's because you've seen a certain character or a certain token, for instance. In this case, if the scout has heard the player, they start to track them. If they see the player from track, they go to chase. Now you notice also that's the same action that if they go from scout to see the player. Now if they catch up to the player, they would go to the fight. If the player is killed, they would go back to scout, and that's the only way they would, because if the player runs away, they go back to track. This is a very simplistic system, and you could see in chase, for instance, if the player runs, they would also go back to track. So this is a very simple system for an AI, but it can have some very intelligent behavior. For example, if a guard or some other enemy AI has spotted the player, it's very unlikely that they're going to just go back to their normal scouting or standing around. Even if the player gets away, they're going to start looking for them. And that's a very intelligent looking behavior, which you can handle with a very simple looking tree. Now, let's take a look at how we would do this in code. So here's our example code. This is the index. We have a series of states. We'll look at those in a minute. We have our state machine, which is just a function. And then we have our object. The object right now is very simple and just contains the particular state that we're starting on, the scout state. The new state, we run our state machine with that object and a context. In this case, the only thing in that context is going to be the distance to the player. In a more complicated system, you might have a more complicated context, or you may have a series of events that you're popping off the top of a stack and processing. And in that case, we log the new state. In constants, we just have our list of states. We have scout, chase, track, and fight. And in our machine, we have a very simple function. Right now, we're just getting this out and we're returning the new state. So if we run this, we just get states.scout. If we are in states.scout, there's a couple actions that we can handle. So if we look back at our diagram, we can see that the scout moves to chase if the player is seen, or the player is heard. What I'm going to be doing is I'm going to be using the distance to player for that. So for example, let's declare some constants. Player heard. If the player is less than 10, they're heard. If the player is less than 5, they're seen. And if the player is less than 1, they've been caught. So we can use this. Oftentimes you would handle this as various actions, but we can also use this to determine various things like this and kind of virtualize those actions. This is actually a place where you could use a switch case, but I tend to like if statements just because they're a little bit more flexible. So in this case, we're going to say, okay, what is the state we're starting in? This is going to be object.state states.scout. Now, if we're scouting, there's two possible places we could go. And so for one, if the player is within 10 blocks, they've been heard. So if distance to player is less than player heard, Then we're going to want to transition the state. So if the player is seen, we transition to chase. So we're actually going to return states.chase. Now this is an example of a state change. So we've got our state here. We're in Scout, something has changed. We return chase. And actually here I'm actually just going to return object.state, because if no action changed, then we'll just return the current state. So if I run that, nothing changes because the distance was 10. But if I switch it to 9, now you can see it's changed to states chase because the distance was 9. Now, even if the player distance goes back to 10 at this point, so we put this, well, let's say 15, our object, our AI, is still chasing at this point because we don't have a transition going the other direction. We could. So we could actually have something states.chase, and we could say if distance to player is greater than 14, we go back to Scout. Now, if we run this, we return to Scout. However, this is not on our map here. This current AI, as long as the player has been seen, they will chase them forever. So I'm just going to take that out for now. We have one other way that we can get out of Scout if the player is heard. So, oh, actually I did this. This should actually be seen, huh? So let's check that. So if distance to player is less than player heard. In this case, actually, we want to return states.track because now we're tracking the player. So if I run this again, now I'm actually tracking. So let's change this to maybe we got a little closer to the player because we've been tracking them. Now we've gone, oops. Oh, yeah. Because I don't have actually this particular state. So we could add that in as well. What that means is I would have like here, else if object.state equals states.track. If distance to player, that shouldn't have been capitalized, is less than player seen. Very similar conditioned up here, right? We go to states.chase. And you might say, well, why don't we just have something simpler where if the distance to player is always, ever if it's less than player seen, we go to that state? Well, there might be some cases where, for example, maybe this AI is wounded, or maybe they're running away from the player because the player is too strong, or maybe they've got a different goal. We don't always want them to fill this. This, again, is a very simple diagram. And, for example, what if something goes wrong with that? Maybe they're actually fighting the player, and all of a sudden the player decides to step back a little bit. They may all of a sudden start going to a wrong state that we don't want them to. This diagram and this way of handling is to make sure that the only behaviors that the system can go into are the behaviors that we've dictated. So you can kind of see the idea here. Basically, we check at the top, what state are we in? And again, a switch case can work quite well for this. I just tend to prefer if statements because I don't like how switch case handles its variable assignments. Then you look and you say, well, is any other case met? In the case of, for example, a regular expression or a language parsing, you may have a system where you have to take a branch from that particular case, and it's actually an error if you don't. In that case, you would return an error at the end here. But here I'm saying, okay, is this true? Has this system changed? Okay, if that's the case, move to a different state. Otherwise, has this changed? Move to a different state. If none of those are true, then we just don't change. We stay in the same state. Similarly for here, we have, okay, we're in tracking and we've seen the player, we go to chase. Could also add another one here. If distance to player is above or equal to player seen, then we would actually return states.track. So if we are chasing and we've lost sight of the player, we would move into this, and that is this bidirectional here. So if we want to look at that, okay, that's moving there. And let's say that the player now starts running and backs off. Well, now you can see we were tracking, now we're chasing, now we're back to tracking. Now here from chase also we can go to fight if the player's caught. Similar idea in chase here. If distance to player is less than player caught, then we return fight. So now if we come in here and we say, all right, let's change this so that the player is no distance. We're right next to the player. Oh, went to chase again. That makes sense. Yeah, so you could see there's kind of an issue there. We actually went to 0. The player just stood still, and we caught up to them too quickly. But because we were in the track state doesn't know how to go to the fight state, because the system says, oh, well, there would never be a case that you'd be right next to them right off of tracking them. Maybe that is a thing. Maybe if the player was lying invisible, and you're trying to track them, but you don't see them, so you get close enough. That's a state we could add in as well. But in this case, that means I actually have to tell it, okay, we got close to the player, and now we've caught them. In an actual scenario where you were using this in, say, a video game for a guard AI, you'd be doing this on multiple ticks. So even if the player was right next to you, you would do 2 ticks. Once you would jump into chase, and then immediately you would go into fight as well, because it'd just be update ticks. Now track, chase, and goes to fight. So that's kind of the idea behind the state machine. It's a fairly simple code-wise, as you can see, but the concept is a little powerful. You can basically make sure or ensure that whatever you've diagrammed out, your world or your system will always follow these rules. This can be really helpful when you're handling complex operations that maybe need to run over multiple cycles. You could also use a state machine for maybe an asynchronous job that needs to update multiple things and react appropriately to various error codes. And as you can see, it's just a function. You pass in your object, or you could even just pass in the state. With a context, this doesn't have to be context. This could also be some action that happened, or the next token, for instance. And based on this formula, where you say, what is my current state? What actions have happened, and what state should I be in based on those actions? You can build a rudimentary state machine. Hopefully this is helpful, and I'll see you all next time.